Thanks for accessing our video, Multivariate Regression Models. My name is Jeff Burris. I'm the founder and principal of Advanced Purchasing Dynamics. Multivariate regression lets us look at a number of factors that influence the pricing or cost of components and develop a should-be estimate. Here's an example of a model that uses net part weight, number of machine surfaces, number of times washed, and a material index value to create a should-be estimate for a component. This was developed using multivariate regression. Why would you want to use multivariate regression? Well, it's a little easier than linear models when you're dealing with multiple variables. Gives you a quick costing tool to be able to see if supplier pricing is in line or identify parts that are not priced like the others. You can also develop them to include raw material indices and track how costs should be moving based upon index changes. For example, let's say you're buying steel tubes and they have different shapes, different numbers of bins, different welding. Using this limit, and all you have from the supply base is price, and you know the physicals about the part, how do you use this information to predict cost or validate a supplier quote? Step one of doing this is you want to look at the physical parts and brainstorm a list of possible cost drivers. Remember, we're brainstorming here, so don't try to evaluate, just brainstorm. Regression is going to tell you which values actually impact price, have the potential to impact price, and which do not. After you've developed those list of brainstormed cost drivers, here's the list we came up with. You want to collect data on a number of parts that are priced. How many parts? Well, you want to have 5 to 10 parts for each variable selected. So if you selected 10 variables that you want to run a regression on, you want to have between 50 and 100 priced parts to be able to run multivariate regression. You want to take and create a data table like this that shows the different attributes that you want to evaluate and what the current piece price is. If you've got non-numerical data like does the part have a finish on it, does the part have a label on it, you can use ones and O's. So in this case, if the part is finished, you put in a 1 in the table. If the part is unfinished, you put in a 0. So you convert the non-numerical data to numerical, then you want to run your regression. Use Excel to run a regression, and up in the links up above, there's a white paper and also a longer 30-minute video that provides more details on how to do this. But when you run regression in Excel, you get a table like this. So we've got all our variables highlighted in orange and something called the coefficients. The coefficients are actually our pricing formula. So the length of tube times 0.210507987 plus the diameter of tube times the coefficient plus the number of bins times the coefficient plus the number of attachments times the coefficient. That's our formula for pricing. So Excel spits this out for us, and Excel also tells us if the formula is predictive or not. A predictive formula will have an R squared close to 1. This one is extremely predictive, and the first time you run a regression using Excel, you're going to come up with something that's very unpredictable, right? You're going to come up with a 0.4 or a 0.3. So when you get something like that, you then want to look at the t-stats, and the t-stats tells you which of the physical part attributes that you put into your regression are actually predictive of cost. A t-stat of greater than 2 or less than -2 is a significant driver or determinant of pricing. One's near 0 or not. To attempt to improve the equation, you do two things. One is you remove the drivers with t-stats that are the lowest. The second thing you do is you run all your parts through the regression formula, and you look for ones that are outliers, ones that are very unpredictable on a part level basis of what the pricing should be. So by eliminating variables where the t-stats are not are close to zero, and by eliminating parts where it's very unpredictable, where you look at the variance when you put it into an Excel formula, you actually improve your formula. You want to continue to work on your multivariate regression until you get an R-squared value that's between 0.8 to 1. You're never going to get one that's totally predictive, but if you're in 0.8 to 0.9, you're really in a good place. If you want more information on this, the links above in the overview provide a link to a white paper on using multivariate to develop should-be cost models, and also to a 30-minute webinar that we did on the same subject. Thank you very much.